Assalamualaikum warahmatullahi wabarakatuh and good day everyone. Today I will be presenting our research title Forward and Optimized Inverse Kinematics utilizing the Levenberg-Marquardt algorithm for a 6 DOF robot manipulator and sorting applications. This work was conducted by myself, Muhammad Hafiz Hasnul Faiz, alongside Dr. Magat Shahirul Amin and Mr. Idris Zainal Abidin. Our research focuses on addressing key challenges in robotic sorting using an affordable hardware and advanced algorithm. The integration of color sorting robots into industrial processes is critical for improving efficiency. However, current systems face significant challenges, including high computational demands and real-time processing constraints. Our work focuses on leveraging technologies like the robot operating system and OpenCV to overcome these challenges. By implementing an optimized approach, we aim to improve accuracy and efficiency in sorting operations. Our primary goal is to develop an efficient kinematic model for a 6 DOF robot manipulator. So this includes implementing an optimized inverse kinematics algorithm to enhance motion planning and achieving a reliable real-time sorting based on color detection. Additionally, we aim to achieve this using cost-effective hardware and robust software frameworks. For this work, we use the DOF pod, a 6DOF manipulator. It is equipped with 6 servo motors controlled through a Raspberry Pi running ROS Noetic. The manipulator also includes a camera with a 640 x 480 resolution for vision-based tasks. This setup demonstrates how affordable hardware can be used to achieve high precision in industrial applications. Kinematic modeling is the foundation of robotic motion. So in this study, we use forward kinematics to calculate the position of the robot's end effector based on the joint angles. For inverse kinematics, we apply the Levenberg-Marquardt optimization algorithm, which minimizes positional errors and ensures accurate motion planning. So this combination allows us for a precise pick and place operations during the sorting task. This system uses OpenCV for real-time image processing. Firstly, the RGB images are captured through the camera, and these images are converted to grayscale-based image to reduce the computational load. Then, a Gaussian filter is used to filter and remove the noise, and the Canny edge detection is used to identify the object boundaries. Finally, the object centroid is calculated by providing a precise coordinate for robotic motion planning. This streamlined process ensures efficient object detection and sorting. This is the summary of the overall process of converting the image into object detection using image processing technique. One of the key challenges in robotic sorting systems is accurately translating visual information from the camera into precise coordinates the robot manipulator can use. So this process, called image to coordinate translation, allows the robot to interpret what it sees and interact with its environment effectively. So in this section, I will explain how our system achieves this using a series of mathematical transformations and equations. The process involves converting the object's positions as seen in the camera's image frame into the robot's base frame. So this ensures the manipulators can move to the correct location to pick and place objects efficiently. To begin, the relationship between the object's position in the robot's base frame and its position in the camera's image frame is described using equation 1. This step captures the object's coordinates as seen by the camera, which are in pixel units, and prepares them for transformation into real-world coordinates. In simpler terms, the camera provides a 2D presentation of the objects, but for the robot to interact with it, we need to interpret its position in 3 dimensions. This equation lays the groundwork for the subsequent steps by defining the object's location relative to the camera. Then, the homogeneous transformation matrix represented by equation 2 is applied. The matrix, denoted as HRC, bridges the gap between the object's position in the camera frame and the robot base frame. The transformation matrix combines two essential components, rotation. This accounts for any angular misalignment between the camera and the robot. Secondly is the translation. This adjusts for the linear displacement between the two frames. The beauty of this homogeneous transformation matrix is that it seamlessly integrates these adjustments into a single mathematical operation. By applying this matrix, we effectively map the 2D pixel coordinates into a real-world frame that aligns with the robot's understanding. Now, let us focus on the rotation component first, which is represented in equation 3. This equation calculates the rotation matrix RRC, which defines how the camera's coordinate system is oriented relative to the robot's coordinate system. For instance, if the camera is mounted at an angle, this rotation matrix ensures that the object's position is adjusted accordingly. Without this step, the robot might misinterpret the object's true location, leading to errors in pick and place operation. This alignment is crucial for ensuring precision, especially in dynamic environments where the camera and robot may not be perfectly aligned. Following the rotation adjustment, equation 4 addresses the displacement between the robot and the camera frames. This displacement, denoted as DRC, is the linear offset between the two systems. For example, if the camera is positioned 10 cm to the left and 5 cm above the robot base, these values are incorporated into the equation to correct the object's perceived location. This displacement can be measured during the calibration process using tools like rulers or laser markers. By accounting for this offset, we ensure that the final position calculations are accurate. Finally, we arrive at equation 5, which computes the object's real-world coordinates. This equation combines the rotation and displacement adjustments into a single step, outputting the precise position of the object in the robot's base frame. At this stage, the system has all the information needed to guide the manipulator's movement. The output coordinates are used by the robot's motion planner to navigate its end effector to the correct location, enabling accurate pick and place operations. The image-to-coordinate translation process is critical for real-world robotic applications. It ensures that the robot sees through its camera is accurately translated into actionable instructions for its manipulator. However, achieving this level of precision requires careful calibration and robust implementation of the equations. One of the challenges we encountered during this process was ensuring consistency in lighting and camera positioning. Even small misalignments or variations in lighting conditions can introduce errors in the calculated coordinates. These challenges highlight the importance of precise setup and regular calibration. Our experiments demonstrated promising results. The servo motors achieved an average absolute error of 0.46 degrees, indicating high precision. The low error rates and minimal jitter make the servo motor suitable for high-precision tasks like pick-and-place operations. The system performance is highly stable under varying loads and conditions. This level of accuracy ensures the robotic manipulator can meet industrial demands where precision is critical for sorting and placement tasks. The end effector positioning had an average error of 1.65 mm, suitable for industrial sorting tasks. 70% of experiments show errors below 1 mm, demonstrating excellent performance for most operational ranges. Higher errors at extended position may be due to physical limitations of the manipulator or increased complexity in motion control. Slight mechanical inconsistencies and system constraints may also contribute to positional deviations. Color detection showed an average Euclidean distance of 57.84 in RGB values, highlighting the system robustness under ambient lighting conditions. The best performance for blue objects has been identified with the lowest error of 8.9%. The higher errors observed for darker and less saturated colors, for example, like a dark gray. The impact of lighting, which insufficient lighting led to discrepancy in detected colors. Variations in ambient lighting also can significantly affect color detection accuracy. While our system demonstrates excellent accuracy and reliability, we identify areas for improvement. Challenges like lighting variability affected color detection, and errors increased when the end effector operated near its physical limits. Despite these challenges, the system's modularity and low-cost design make it highly adaptable for various industrial applications. So, in conclusion, image-to-coordinate translation is the backbone of our sorting system. By using equations 1 through 5, we have ensured that our robot can interpret visual information and act on it with high precision. This methodology not only enhances the robot's accuracy but also allows for adaptability in different environments. With further refinements, such as dynamic calibration or adaptive lighting, this approach can be extended to more complex scenarios, including handling irregularly shaped objects or working in unstructured environments. We would like to express our gratitude to the School of Electrical Engineering at University Technology Mara for providing the facilities and support for this research. Additionally, we thank our collaborators for their valuable contributions, and thank you for your attention.